Pretty much on the first page, problem started with number 4. Main thing with number 4 was that you weren't getting your units correct. For example, if you had a density, which is in grams per milliliter, you would multiply it, or some of you would multiply it by grams to get milliliters. When actually, if you were to multiply this out, you would get grams squared over milliliters. So you have to be very careful with your units. The most common mistake in terms of units was when you were dividing. For example, if you had milliliters divided by grams per milliliter, the milliliters do not cancel. This is actually the same thing as milliliters over 1 times milliliters over grams. Getting milliliters squared over grams, so they don't cancel. So be very careful with your units. Also for number 4, when you had to find the total volume, you had to just find the volume of each one separately, and then put them together. And when you had to find the differences between two masses, first of all, you had to make sure you're actually solving for mass and not volume. And then once you found the mass for both of them, you just had to subtract one from the other. For 4C. 5 was pretty good. 5B, we went over this right before we took the test. If you hung 2 identical springs head to tail, it would be more stretchy. It would not be as rigid. It would have a lower spring constant, smaller spring constant. The spring constant tells you how rigid or how strong the spring is. Number 6 on the back was probably the most missed question. All you have to do in the last sentence, it says, figure out the cost per surface area. So all you have to do is put a $ over the surface area for each one. I will also accept surface area per cost. But essentially, you just had to find the surface area for the different radiuses using the pi r squared formula that they gave you. And then having the price go either price divided by the surface area or the surface area divided by the price and compare. If you did cost per surface area, then the lower cost would be a better choice. If you did surface area per $1 or per cost, then the more surface area per $1 would be a better deal. Does that make sense? So you had to kind of analyze what you got from your comparison to know which one was actually a better deal, depending on if you did cost per surface area per cost. For 7, the main thing here was just units, not putting centimeters squared to centimeters cubed. Also for part D, if it was made out of cardboard and foam, which one would hit the ground first? The bigger one would hit the ground first. This was just like the styrofoam ball experiment we did. When you dropped it, the one that had more volume and not as much surface area hit the ground first. Because the less surface area to volume interfered with the air, interfered with the wind resistance less. Does that make sense? Not as much surface area to its volume. And then 8 was actually pretty good. Not a lot of problems with the question. Multiple choice on the back is where a lot of points are missed. Because of time today, we'll have to go over those another time. But if you look at the front again, you have a percentage and then you have a number next to the percentage. The number is half of the percentage because it's out of 50. But we're going to take this instead, out of 50, it's going to be out of 48, which is going to raise your percentage a little bit. So take whatever smaller number you got, and take that divided by 48 instead of divided by 50. And that's going to be the recorded percentage.
So the problem is zero.
Yeah,
these are good problems.
No, this time it doesn't. Oh.
Was it like 48?
Yeah.
Are there any questions now about the test or about the homework?
4%.
If you don't have any questions, then you can pass back your tests. So turn them into one person in your table and I'll collect them.
Okay.
Alright, so if you look at the backboard, there's where we're gonna, everything we're gonna do today, this syllabus for today. So the first thing we're gonna do is the book example, because we're gonna be learning about pressure today. And then we'll talk about water pressure afterwards. So the book example with pressure, you guys all have your physics book, hopefully.
I know.
Or at least share it with your tables if you don't. What we're going to learn today is pressure. So, we have to come up with a formula for pressure. If I hit the table with some force, actually, I'll do this instead. Who wants to come up and be a volunteer? You want to come up? Yeah. All right. So put your hand right here. Just flat. Yeah, just flat. Now, if I was to, no, I'm kidding.
There goes his baseball
All right.
career.
Now, what would you be more scared of? This weight lying in your hand like that, or having the weight be on the tip of this pencil lying in your hand like that? The pencil. Okay, why? Good. Less area, and so there'd be more pressure. Good. All right, you can sit down. Good. So we found out this is a safety. This is 1 kilogram. That didn't change. What changed was the area. I put the kilogram on his hand, and he didn't mind that. But he would have minded if I put the pencil on it. It could have punctured possibly. But if I put a larger mass, it would have been more pressure, and the smaller area also made less pressure or more pressure. So pressure is just the force over the area, and in a lot of times on Earth we just call force weight over area. So either way, the weight or the force divided by the area. The more force, more pressure. The less area, more pressure. And we're going to demonstrate this with your physics book. So the first thing I want you guys to do is we're going to figure out what is the area of the big side of your physics book. And to do that, you'll need to measure with a ruler. So everybody come up here, grab a ruler, and measure it with centimeters. For you. But when you
grab me one?
I have it to my table only, and very nice to meet you.
Thank you.
You can do it one per group.
When you measure for the area, for both lengths, make sure you use meters.
Centimeters?
It's going to be measured in centimeters. You'll need to convert it to meters when you take the area.
Write it down.
So you'll need to take the measure the length and the width. Alright, so what did you guys get for the flat side? For the area?
Oh, they're still working on that.
So 20.8 and 46.
So you got what?
26 centimeters.
Okay.
Make sure you convert both measurements to meters
No,
before you
not yet.
multiply.
20 meters. And then you gotta find the areas with it.
Point zero, point four.
Because it's length and width, isn't it? Okay, so,
Alright, so what'd you guys get for the area?
That's it.
0.054
.054
meters.
meters squared.
Squared.
Does everyone agree with this? Yep.
Did you guys
Okay,
get
good. So now we're going to assume that the mass of your book is 1 kilogram. So what, we have the area, we're trying to find the pressure. So how do we find the force to get the pressure? Yep, so force equals mass times gravity. So then we have the mass is 1 kilogram. Gravity, we'll just assume is 10 meters per second squared. So then, what does the force come out to be? 10 newtons. So then, the pressure of, I'll say the flat side, I'll just say PF, pressure of the flat side, would then be the 10 newtons divided by the 0.054 meters squared. What does that come up to be? 185.19. 185.2. And what's the units going to be in? Newtons per meter squared. So newtons per meter squared is the same thing as pascals. That's the unit for pressure. So 185.2 pascals. So now we know how much pressure that book would be exerting onto the table if it was laying on its flat side. But now instead of laying on its flat side, what happened if you tilted it up so it was on its binding? It would have less surface area. So let's calculate that one. So measure now the length and the width of the binding side.
So it's still gonna
That's
be
what-
the
that's what it's saying.
same length, so just measure it.
What?
So it's 0.35.
3.5?
For the meters.
Oh, meters?
Yeah.
Well, wait a minute, that'd be 30 centimeters long.
No, 3.5
Centimeters,
centimeters.
Which
so
is-
it's
zero.
0.035.
Right.
Just forgot to add the zero.
You see what I mean? Because
Yeah.
point 3 would be 30. It's gotta be 0.03.
Okay. Does he want us to find the pressure? Oh yeah.
Oh, you can, because that's the thing to do. Pretty easy to do.
Alright, so what did you guys got for the area of the binding side?
0.0091.
0.0091.
Get that?
Does everyone agree with this one?
Wait a minute.
What do you guys get?
I got .007.
Okay.
0.007.
Yeah, I remember. Let's see.
Is that what you got?
Or not? We're all getting different.
0.007. Does that seem right?
Sure.
Let's go with it.
Well, I don't care. It's fine with me.
Does everyone agree?
I agree.
Alright. What is 0.007 less than or greater than this area? Less. So it seems like it's a good choice. So Does the mass of the book change by tilting it outside?
No.
No. Does the force of gravity then change for the whole book by tilting it outside? No. So we can still use the same force. 10 newtons. But now this time we have a different area. The 0.007 meters squared. And what does that come out to be for the binding side?
1,428.6.
Pascals. Good. Now look at the difference in pressure. Which one has a greater pressure? Binding side. So that just goes to show you that numerically we can look at the numbers and see that we didn't change the mass of the book, but just by changing the area, the pressure increased quite a bit.
Back to it.
So the less area, the more pressure there is. So now that you know that, you have a little bit of an idea of what pressure is. Let's turn into liquid pressure. I'll ask you guys a question. You guys will choose as a table what your answer is going to be, and then tell me in a couple minutes. So the question is, if you are swimming 10 feet deep in either a swimming pool, a pond, or a lake, are they all going to have the same pressure? Is the lake going to have a higher pressure? Is the pond or is the swimming pool going to have a higher pressure?
It's all the same depth.
You're 10 feet on each of them. The swimming pool has walls on the end of it. The walls can't move. The lake doesn't pretty much have walls. So just talk with your table. We'll come back to it in a couple minutes.
You got a choice of swimming pool,
No, but like a lake is more like.
right?
I don't know. I guess whatever has like the most.
All
I don't know, maybe I'm like.
I just want to make sure.
And the reason why. So, what do you say?
I think so.
Who?
But if the area is bigger, the wouldn't, the ducks, that would have to get bigger too. No, they're inversely
Inversely.
they're inversely
Yeah,
proportional.
talking about how we're gonna
So would
guide
it be the opposite? So would it be
We
like,
got.
I don't
Can't
know.
help. Well, you know, that's
No, my head is further.
Your head always hurts right
I was
now.
actually.
Why would you swim? I was like,
No,
In there, the good thing about it is, I'm
Alright, so
over here,
people around the
you're not
tables.
gonna get sick.
As soon as
Next
everybody,
thing is, you're not being graded on. You know what I mean?
So that means that you're siding with him.
I didn't side with
Yeah,
anybody.
you did. You definitely just sided with him.
If I had my choice, I'd side with you. No,
alright, we're gonna start with table 1.
I don't know what he's saying.
So table 1, what was your conclusion? What would have the highest pressure?
The swimming pool
Swimming pool, why?
is smaller
And why would they have more pressure?
smaller.
because you're reducing the area.
Okay, good. So you're reducing the area,
The bounds on it too.
or the volume.
No.
Alright, table 2.
Well, we said lake because it had more area.
Okay, lake because of more area, so we'll talk about both of those. Table 3,
We said like two.
Why?
Reasons.
more area. Okay,
Cool.
Definitely the pool,
why?
because it's a smaller area.
Less area.
That's what I'm talking
So
about.
we have
Less area,
competing
so there's,
opinions
so
on
there's
this
small,
area here.
there's more pressure, it affects it greater.
Okay, table 5. All the same. Why?
Because with water, it's got different consistency, and it's for the same reason why NASA used a water pool for zero gravity for space training. Gravity would have no effect on it.
Okay, but besides gravity, we're talking about pressure.
Right, but for the pressure, it was the mass times gravity.
So that was the fourth part of it.
Okay.
So you're right.
Yeah.
You're wrong.
Okay, so they say all the same. And what about table 6? All the same why?
Because it doesn't matter how much water the person is in, it matters how much is above them.
So you're saying the only why that matters is what is above you. Okay. So now, the first thing we have to go over is this area thing. Some of you said more area was better, some of you said less area was better. Let's look at the formula. Based on this formula, if I reduce the area, does the pressure decrease?
No. It increases.
It increases. Like we just saw, we reduced the area and the pressure increased. So a smaller area would have a larger force. But when we're talking about water now.
Yeah.
And if, imagine, I'm going to take the whole volume of water and imagine that that's this table. And this is the object on the table. Now the table is putting a certain amount of pressure onto this object. But is the whole table putting pressure onto this object?
No. There's like hard.
Only what's under the object is putting pressure onto the object. If there was a little part of the table that rose up, and I put that on there, wouldn't it have the same amount of pressure? So the surrounding area doesn't matter. Just like in a swimming pool, all the surrounding volume around you doesn't matter. And table 6 was right when they said only the vertical column above you matters. Only the water that's above you. And we can actually prove that. If we look over here, we know that pressure is weight over area. And what do we know weight is? Weight is just a force. So another way to express it is newtons. And how do you get there? So the force or the weight is equal to mass times gravity. Good. Force is just equal to mass times gravity. So we'll say that the weight is mass times gravity over area. Does that make sense so far?
Yes.
All you do is convert the weight into mass times gravity. Now, we also know that density is equal to what? Density is mass over volume. So solving for mass, we multiply volume to both sides, and we get density times volume is the mass. And I'm gonna substitute the density times volume in for that mass right there. So now we know that pressure also equals density times volume, which is the mass, times gravity over area. Still make sense? Just substituted two variables so far.
For one.
Now what's the next step I can do? How do I cancel out this area?
Multiply.
Well, if I have this density here, and now how do I get volume from an object? Area times. For example, if you looked at your book and you calculated the area of this flat side, but you wanted to get the volume, what would you multiply it by? The width. The width. In this case, the area would be the bottom surface of like the lake or whatever we're talking about, or wherever you're standing on. And what you multiply it by would be the height. So the volume would turn into the area times the height. Canceling out at the bottom, the denominator. Does that make sense?
So the areas aren't there?
They just cancel out when you're talking about the pressure. So that for water pressure, all that matters is the density of the object, or is it whatever what we're talking about is water in this case. The density times the height above you, all the water just pressing down onto your head, times acceleration due to gravity, and then nothing on the bottom. So it's pretty much just the weight density times the height, or density times height times gravity. But what's important is that the areas don't matter, they would cancel out. So that all the water surrounding you doesn't make a difference. The only thing that matters is how much water is above you. So a deeper lake will always have more pressure than a wider lake of a lower depth. Does that make more sense? All right.
And that also applies to air pressure too, doesn't it?
It does.
Yeah, and you know, I mean, as you guys go up and down in the hills, you can feel the, you know, valleys, you can feel the difference in pressure. And why is the difference in pressure? It's due to the amount of air above you, right? So, yeah, so that makes sense. I should.
Did you forget the camera was on?
Yep, it is. But, you know.
And now there's an interesting example. Now that we know about liquid pressure, regarding dams. So here's a dam, and here's this water. Now this water is exerting pressure on this dam. If you think about it, whenever you're in a pool and you go down really deep, do your ears start to hurt? Yep. So that's just because of the pressure that's on them. When you think about it, when you're down like say 10 feet, you know that's more pressure than 5 feet. But if you're down 10 feet and you turn your head, does the pressure change? Does it feel different?
Yes.
No.
Yeah, it only matters when you go up and down. So turning your head doesn't make a difference. You're still at the same depth. But that's important because the pressure is going into your ears. So it seems like no matter which way your head's turned, there's pressure from every direction onto that surface, which is your ear. So in this case, there's pressure directly onto this dam, sideways. And the bottom is going to have more pressure than the top. And especially if there's so much pressure that there's some water particles that get underneath the dam, well now that's kind of like having a board on the floor, but putting like little balls under it, like metal balls, so that the board can just roll around. That can make this dam a lot easier to move. And if it was built like this, the water over time could eventually push the dam and break it. So we don't want the water to move the dam. So the easiest solution would be to get a big lead weight or some other heavy object and put it right on top of the dam, pushing the dam into the ground hard enough so that it won't move. But there is an easier way. We don't have to use a weight. If we just build the dam a little differently, we can actually use the water pressure, the thing that's pushing the dam away, to actually help keep the dam in place. Does anybody have any idea how they could build a dam so they could do that? Notice that the bottom, again, because it's deeper, the bottom pressure is greater than the top. How can we secure that into the ground?
Make it swoop.
Good, make it swoop. So instead of building the dam vertically, we can build it with a swoop. So now we have the same water pressure. But now, when it gets to the swoop, remember when you moved your head in the water, you still felt the same pressure. It was directly into your ear. It wasn't sideways into your ear. Your ear didn't go up any bit. It was directly into your ear, completely perpendicular to the side of your face. So it's going to be completely perpendicular to the sides of that dam. And the strongest forces are going to be the ones pushing it downward into the ground, while only the weaker forces are now going to be pushing it sideways. You'll never see a dam built vertically. So, since it's a shortened day, we won't have time to finish the lab, but we're gonna start it. Basically, you come up here and grab these 2 sheets. The third one's going to be homework, so grab that one as well. And we're gonna be talking about Archimedes' principle. So Archimedes' principle has to deal with pressure and buoyancy, but this will be the directions, the white sheet. Do not write on the white sheet, only write on the yellow sheet. This will be where you record your data. Today, I want to get through the data recording, because the calculations can just be done with that data. So we're just going to get through the data recording, and before you come up here to grab the sheets, I need to show you a few things. The first thing is, with the balance over here you're going to be working with, before you start, someone from your group of 2, come up here and look at this paper clip. It's not on the big thick wire going this direction. It's on a very thin wire going the other direction, and on the bottom one, because there's 2 of them. So make sure you put on the right wire, or else you'll get really inaccurate readings. So just come up to look where it's placed. The other thing is, you're going to be measuring masses, and you're going to be using the paper clips to do it. The paper clips also have a mass, and the paper clips, we cannot record their mass also. So you'll first have to find out how much your paper clip weighs. It should be around a gram, and then from each of your measurements, you'll have to subtract away that gram. Make sense? Also, we don't have enough weights for everybody, so only take a couple at a time, and then when you're done with those, put them back, so that everybody can get around to the weights before we leave. And then when you're done with your chart, go over to Mr. Merrick, and he'll check to make sure everything looks right. You didn't make any mistakes.
You can ask him, I'll tell him the secret.
All right, so you guys can go. You're working with partners. So come up and grab the paper.
follows murder so funny. Sarah,
They kept telling us to be quiet.
so you start building it in. Like when they split the water and then turn it. I don't know.
So there's murder.
And then you need a ring stand, so make sure
When you actually go after the
What's going with the smart idea, huh?
or when they do
Grass aluminum lead burning.
Hey, Brandon, did you get a paper clip? Okay. Oh, wait, we didn't get the math.
Alright, it is 270.